imagine breaking a mathematical barrier. I mean, one that stood for centuries, allowing us to describe numbers, operations in ways we just didn't think were possible before.
Yeah, it's pretty wild.
So today we're diving into this really groundbreaking research paper. It's just out in PLOS 1, and it introduces something called generalized hypercomplex numbers.
Right. And these aren't just, more numbers. They genuinely seem to extend how we understand numbers existing and interacting.
Yeah.
Across all dimensions.
All dimensions, okay.
So our mission for you today is really to get into how these researchers found this unique way to create them. What makes them so different, fundamentally different, from the systems we know.
And why it matters. Right, like what doors does this open?
Exactly. The potential in theory, but also maybe in applied fields too.
Okay, let's set the scene a bit. Because for a long, long time, mathematicians pretty much believed there were only 4 special kinds of number systems. Normed division algebras, they call them.
Right. The real numbers.
Yeah. You've got your basic real numbers. That's 1D. Then complex numbers, 2D.
Familiar territory so far.
Then it jumps, right, to quaternions at 4D and octonions way up at 8D. And these were systems where, everything non-zero has an inverse, and you can measure its size.
And the crucial thing, the thing that became dogma almost, was that theorems proved these were the only ones, which meant certain dimensions, 3, 5, 6, 7. They seem totally off limits for this kind of well-behaved number system.
It was like a mathematical wall.
A very solid one, yeah, backed by proof.
And this isn't just some recent puzzle. You have to think back to William Rowan Hamilton, 1843.
Oh, yeah, the bridge guy.
Exactly. He was desperately searching for a 3D algebra, like a number system for 3 dimensions.
But he couldn't find it.
No. Instead, he stumbled onto 4D quaternions. And he was apparently so excited he carved the basic rules, that famous T tot dollars, J2 dollars, TTIA2 I tau right into Brumbridge.
Amazing. But those quaternions, revolutionary as they were, came with a catch.
A big one. They weren't commutative.
Right. A times B is not necessarily B times A. Order matters, which is weird for numbers.
And then octonions, which came later, were even stranger.
Oh, yeah. They were non-commutative and non-associative.
Yeah.
So even how you group things, like A times B times C, might not be the same as A times B times C.
It really felt like a fundamental trade-off. To get to higher dimensions, you had to give up these basic intuitive properties of arithmetic.
That was the established wisdom.
But this new paper says, hold on a second.
Laughs slightly, yeah, basically.
This is where it gets really interesting. They're proposing these generalized hypercomplex numbers that, they claim, can exist and operate in all finite dimensions.
All of them, including 3, 5, 6. All the ones that were supposedly forbidden. It's a huge theoretical claim. It patches that centuries-old gap.
Okay, how? What's the trick? Because something fundamental must have changed.
It is fundamental. Maybe a bit mind-bending at first. The key insight, the sort of radical move they made, was to relax the distributive property.
Wait, distributive? Like A times B plus C equals A times B plus A times C, that property.
That exact one, the one we learn in elementary school. They found that if you allow multiplication not to distribute over addition in the standard way.
That sounds completely wrong. Like, how can that even work?
Well, it sounds wrong, but it's precisely what let them break the dimensional barrier. It's like finding a loophole in the rules that everyone thought were absolute.
Okay, so they break distributivity. What do these numbers do then? What properties do they have?
This is the really surprising part. Even though they're non-distributive, this new multiplication, they call it spherical multiplication, or SM. It's still commutative and associative.
Whoa, hang on. So quaternions and octonions lost commutativity and associativity in higher dimensions.
Right.
But these new numbers, despite messing with distributivity, they keep commutativity and associativity in all dimensions.
That's the claim. Commutative, associative, and it still preserves the norm, the length of the numbers. And it forms an abelian group, which, just means multiplication is commutative. Order doesn't matter for multiplication here.
That feels like having your cake and eating it too, mathematically speaking.
It kind of does. And that spherical multiplication name isn't just random. Geometrically, they show it relates to constructing a sphere. It's quite elegant, visually.
Okay, and you mentioned another practical point, something about polynomials.
Yes. This is another really neat consequence. Remember how with quaternions, a simple polynomial, like degree 2, could have infinite solutions, which is not very helpful sometimes.
Yeah, a bit messy.
With these new hypercomplex systems, polynomials behave much more predictably. a polynomial of degree and has a finite predictable number of roots.
How many?
Specifically, $2 roots if any is odd, and $2 and plus no roots any is even. Much more manageable.
That alone seems like a big deal for actually using these things.
It could be. And the paper does suggest some potential applications beyond just the pure theory.
Like what?
Well, they propose it as maybe an alternative way to express quantum states, alongside the usual superposition idea.
Interesting. Quantum mechanics.
Yeah. And also, potentially, in things like point cloud image processing.
Yeah.
Anywhere you're dealing with lots of multidimensional data points.
Okay. So let's recap. By taking a foundational property, distributivity, and saying, what if we just relax this a bit?
A daring move.
They've potentially opened up this whole new landscape of numbers that work in all dimensions, keep some really desirable properties like commutativity, and might even have practical uses.
That's the gist of it. It really challenges those old boundaries, offers some fascinating new mathematical tools.
It really makes you wonder, doesn't it?
What's that?
But what other basic rules, what other fundamental assumptions in math might be worth questioning or just tweaking slightly?
That's a deep question. If relaxing distributivity unlocks this, what else might be possible if we look at the foundations again with fresh eyes? What deeper structures are waiting?